So today is a very short lecture, so you will have a lot of time to work on. So it is about image histograms. So an image histogram is a count of how many times you have seen values of a particular value. So intensities of a particular value. So let's say that we have this image, like images, if you encode them with 8 bits, the gray level, it goes from 0 to 255. And then you count how many times you have seen the value 0, how many times you have seen value 1, 2, and so on. And switch off. So how many times you have seen each one of these values? And this is simply, okay, you have seen it 3 million times, a value about 50. So, and we understand why. This is a very dark image. So most of the pixels will be dark. Dark are those low values. And then the few pixels that are white will be here. So this is simply counting how many times you have seen each specific value. Okay, now what about this image? So this image, again, you count, and now there are a few things that we notice. So the first thing is, okay, so let's try to understand this part. So we have two regions. One is darker, the other one is brighter. So looking at the image, we see the darker region is probably, actually there are two dark regions. So one will be the tree, the other one will be the ground, and the brighter region will be the sky. And that is also something when we compare this histogram to the previous one, that is, these histograms seems to be limited. So the minimum is not 0, but sorry. The minimum is not 0, the maximum is not 255. So it seems that there are ranges of intensities that are not used. So this was opposed to this one. This one, there are something very dark, so it is almost going to 0. And then there are some very few, but very bright points. So we are using the full dynamic range of the intensities. And this one is not. There are empty regions, and we could exploit this further, so we can increase the contrast. Actually, the contrast of an image is the difference between the maximum and minimum value. So here, there is much less contrast than in the other one. So this is almost all not the same color, but much more similar colors than the other image. So contrast is the difference between maximum and minimum. Here we have another image. So here it is the opposite. We have very few dark colors. Most of it is white, and we have different kinds of white. So one will be the snow, one will be, I don't know, the sky that is bright but not as bright, and so on. Here we also see a feature that we didn't see before, that is saturation. So you see, it is as if the histogram wanted to continue. It is cut at 255. Then all the pixels that would have a higher intensity, somehow they are limited to 255. So, and this makes sense. If you think of how the image is formed, so the image is formed in this way. So you have an object, real life. So you have an object, then you have a lens, and this lens projects onto an array. So this is an array of sensors. This is an array of sensors. There are many kinds, but say there are CCD sensors. So there is an emits light, and the light is focused on the array. Okay, so each one of these sensors that are representing the pixels, they and making a count of how many photons are arriving. Okay, so there will be a response. So the input is the intensity of photons, and there will be a voltage in the array. And this voltage will be more or less the response. Let's say that it is linear. And you know that this linear response, because in the computer we don't have all possible values, it is discretized in 250 steps. So all these will be rounded to 0. All these will be rounded to 1, 2. So there are two responses. One is the voltage. The voltage is in volts. But then this voltage is translated into an intensity value between 0 and 255. And we do that in 256 steps. So it makes sense that, let's say that this is our maximum voltage that we allow, but we have an image that is saturating, is sending more photons than the maximum voltage that you allowed. Then there will be a saturation. There will be pixels that are receiving more light, but because the sensor is saturated, all these pixels, they are clipped to the maximum value. Good enough? Yeah. Okay, so next. We have color images. So far we have worked with gray images. So gray images, we only have a channel. So we only have a matrix of numbers. But when we have color images, like this one, now we have three layers or three matrices of numbers. Let us go in here. So when you have a color image, you have these three images superposed. One is the R channel, the green channel, and the blue channel. So the red, green, and blue channels. And each one of them, they're made of a matrix of numbers. So now you can compute the histogram for each one of the channels independently. That is what we are doing here. And now we may try to figure how these features map onto the color image. So for instance, we see the sky. This sky is blue, light blue. So probably it's this big blue one, Gaussian mode there. And then for the rest of the image, you don't need so much blue. So that means that you need low values of blue, and that is why you get this big band here. And the image, the mountains, they are mostly red, and they are all kind of reds. So the red channel is more or less flat. Some of them are saturated. And then the green channel, we don't see so much green, maybe a little bit here. So it is probably this region, and then we don't need so much green. So for the green channel, we need low values again. Good. Okay, more images. So this one is the opposite. We don't need so much blue. We don't need so much red. So we need for the blue and red, we need low values. And most of it is green. So we need high intensity values. Green is the one from which we need the most. Yeah.
I don't see any red.
You don't see any red. That is why. So let's say that you don't use red at all. So if you don't use red at all, you could have a delta here, meaning red is 0. But even if you don't see red, to get this kind of stone color, you need a little bit of red. Actually, something interesting is for white, you need the three colors at the same time.
But wouldn't you need them in their maximum intensity?
Yeah, probably they have something here. Actually, there is a little bit going on. Okay, so yeah, for examples. So we see that the blue channel has some saturation. It has a saturation almost on both sides. This one and this one. So this one is saturation. This one is, we don't need blue at all. Okay. So there must be some regions, especially these dark regions, this very black region for black, you don't need any color, so it should be zero. So actually, I think we haven't seen this yet, but I don't think we have seen it. So in the RGB, sorry, so you have RGB, and then any one of them can take any value. But let's say that we put the same value for the three of them. So it is a vector, the same value. So this E is a value in 0, 1. So this one is a gray. It's a gray color. And this gray color may go from 0, 0, 0. This is black. To 255, 255, 255. This is white. Very intense white. And then you have all the colors in between, all the gray colors in between black and white. Okay, so this image here has some black regions, or relatively black regions. That is why you have this delta here. And some of the blue pixels, they are saturated. So that is also why you have that delta. Okay, more examples, but more or less the same. There's nothing new now, basically. Okay, so formally, a histogram is just a count. So the notation here is not extreme, very, very good. So these bold letters are vectors, and the gray image is not a vector. So this should not be bold. So this is simply saying, so what is an image? So we say an image, let's say that it is a monochromatic image. So we say an image, so that is this tree. This just not to get it too clumsy definition. So this is a vector, and I would say it goes from z squared to 0 to 55. Okay, so it is something that takes an image is a function that takes a coordinate and gives you the gray value for that coordinate. What is a histogram? The histogram is another function. So when I compute the histogram of y, now let's see how it looks like. So the histogram is, here we have gray, here we have count, how many times we have seen that gray. So this is a function that takes a gray value. You may remember I'm using square brackets to note discrete variables. So the gray value cannot take any possible gray value between 0 and 255. So for instance, it cannot take 0.2. Okay, so either it takes 0, or it takes 1, or it takes 2, but it cannot take 0.25. Okay, so these are square brackets. So this is a function that takes values in this set and returns values in this set. Sorry. Takes values in 0 and RC. RC is the total number of rows and columns. Here I was lazy. I didn't want to be lazy. Then you have to write here, you have to substitute. It's by 0, 1, R minus 1 times 0, 1, C minus 1. Okay, but this is too complicated. And sometimes you want to emphasize that it is, has a finite support. Sometimes you don't need to specify that. Okay, so the maximum count that I can have, let's say that all my image is full of, I don't know, 2s. So for 2, I will have a delta. For 2, I will have a delta. And this delta will have this, and also, let me be correct here. So this one is this kind of deltas. And I'll explain you the difference now. So, and for all the other values, takes value 0. So it is a discrete function up to 255. So if everything is full of 2s everywhere, so at 2, I will count RC pixels, while for all the others, I will count 0s. Okay, probably this you know already, but let's make a reminder. So what is the difference between this delta and this delta? So this delta normally have to plot like this. This one don't have to plot. Okay, can you tell me what is the difference between these two?
Discrete.
Sorry?
Discrete.
And
Continuous.
discrete and continuous. Yeah. So this is for discrete signal. This one is for discrete signals. So we have this one, and this is for continuous signals. And the names, these are called, it is called Dirac's delta. And this is called Rodriguez. Okay, so let's put some numbers. So let's denote, this is a note. So this one, delta n. Actually, this one here. Okay, I will define this one, and later I will define this one. So this is 1 defined 0, and 0, 0 other values. So if n is different from 0. So this one is delta of n minus n. You're familiar with all this, right? Also you too, Marika and Francesca, you're familiar with these things. Okay, what about this one? This one, actually the definition of Dirac's delta is a little bit more complicated. So the Dirac's delta, there is no way to define it as a normal function. So actually it is not a function, it is called a distribution. This is called a distribution. That is not, it is not a statistical distribution in the statistical sense, but still it is called distribution. So this distribution is such that for any function, for all signals, delta is defined such a way that minus infinity x delta potential of delta, this is x of 0. Okay. So this delta distribution, we cannot define really definition like this, but we have to define it indirectly. And the definition is this. It is a function, if you will, is something that when you multiply by another function and you integrate from minus infinity to infinity, you always get the value of x of t at 0. That is the definition of this delta. And then this one here is delta of t minus t. Okay, so yeah, all this digression came because our histograms are made of discrete signals. So either it takes value 0, 1, 2, 3, but it cannot take values in between. And then it is a function, so a histogram is another function. So everything are functions. And if you want, you can find the histogram operator. So, histogram operator. Let me do some fancy H. Okay, so this is a fancy H. The histogram operator is a function that takes a function and returns the histogram of that function. So you see, you can think of it as, so in terms of systems, you have I is a function, then it goes through this histogram operator, then this one produces h y. Good. Okay, so far so good. So you have to distinguish functions from operators. This is important. So operators are entities that transforms functions into functions, while functions transforms a domain into a range. Okay, so a set into another set, makes correspondences of points between two sets. Okay, so this is what is explained here. So it's simply counting how many times you have to particular value. Okay, so I don't think there is. Yeah, in these slides, because he's working with MATLAB, then he has to deal with G minus 1. And so this minus 1 is because MATLAB starts counting at 1, not at 0. So some of the minus 1s are related. We don't care about these minus 1s. So we will keep more the mathematical definition of it. So let's look at this image. So now we know how to compute this thing. So it is simply counting how many times you have seen each one of the pixel values. You see here the +1 coming from MATLAB. And let's keep doing more operations on it. And let's try to understand the different properties of this counting. Okay, so let's say that we have this image in true color. So true color, you may remember, it is just specifying the RGB channels for each one of the pixels. And for the sake of simplicity, let's have a 16 level 4-bit image. So let's say that have an image. This is an image, a big image, okay, only with 3 pixels. Then these values here, so we say they will be encoded with, here will be loose again. So this is same, right? But we encode these values, these correct values, we encode them with 3 bits. So 4 bits. So with 4 bits, which are the possible values for contain, like 0, 1, up to 15. So in general, if you have k bits, you can take all the values of 0, 1, and k minus 1. So if you have 4 bits, it would be 15. If you have 8 bits, you can go all the way to 55. Okay, so now we have only 15 values or 16 values. So now we can decompose this image into overlaying images. So let's construct an image with only those pixels that have gray value equals 0. So here, just to make it more complicated, the background is white and the selected pixels are black. Okay, so all the pixels in black, they have the value 0. And we see that they are in the very dark areas of this bag. Then all the values with pixel value 1, here they are shown in black. And then with pixel value 6, and then with pixel value 15. So 15 is the brightest point that we have in this image. So we see that here is white spot of the bag. And then it is simply counting how many pixels are selected here, 600. How many pixels are selected here? 2500. Here, 2900. Okay. So now we see that we can decompose a gray image to a series of overlying masks. So all these masks, they are choosing those pixels with a specific value. Any questions? Okay, and then you can count. Simply count. Take each one of these masks and we count. Here you have the counting. So for G equals 0, you have 2900. So for G equals 0, you have 2900 and so on. So looking at this histogram, you say that most of the image is kind of bright or dark. Many more bright pixels than dark pixels. And yeah, this is bright. So you have all the background, all the background is bright. So. Okay, good. So what about coloring? Well, when you have coloring, what you can do is the histogram of each one of the channels. So compute three histograms. So you have this color image, and then you compute 3 histograms, one for the red, one for the green, one for the blue. We haven't defined this yet, the luminance, but you can think of it as a black and white version, as a grayscale version of the original image. Okay, so here, this is not luminance, it is called value, but yeah, it makes, it illustrates what we want. So you can, let's say that you have this color image, and you want to produce an image that is grayscale. So one possibility, you have to reduce that three images to just a single one. So just the possibility is to compute the average of the 3 channels. So you compute for every pixel, you compute what is the average between red, green, and blue, and that is your intensity at that point. And this way of computing, of summarizing into a grayscale, it is called computing the value. Okay, so what about luminance? Luminance is defined in this way. So instead of, you see these red, green, and blue channels, they have the same weight. So we make equal weight of each one of the 3 channels. Okay, then instead of the luminance, is kind of similar idea, but now using different weights. So we will give more weight to green, and later in another lecture we will see why. So we will give more weight to green, a little bit less weight to red, and then the least weight will be given to blue.
Are you going to explain in this class if it's for making a question or not?
No, you can pose your question and
I mean, that is not have like double of green.
yeah, receptors.
Yeah.
Yeah.
So, for seeing the reality as it is, didn't we have to put more in the blue?
Yeah. So it depends on what you want to measure. So there are two objectives here. So one is to make pleasant images. So if you want to make pleasant images, you want to please your receptors, and then actually, yeah, this scaling, this NTSC, you don't know what it is, no? Do you know? No. In the 30s, when the television was invented, there was only grayscale television. That's fine. But then in the 50s, something or 60s, color televisions started, and they had to somehow live with the grayscale television. So they needed a standard that could accommodate the grayscale and the color television. And then they needed two signals, one for the grayscale, and they came out with this luminance, and then another one for the color television. So color television, it was just the 3 channels as they are, and then that's it. But you had to convert the RGB into a grayscale that was pleasant, and then the way to convert it was this one. And the reason is that we have, as he says, we have more green receptors than red receptors, and we have more red than blue. So we are not so sensitive to blue. So if the objective is to display and have some nice images, it is better to do it like this. If the point is to measure how many photos are coming from a point, it's better to give equal weight to all of them. Okay, so so this is the way luminance is defined, and then once you know how to construct grayscale images, you can compute the histogram of that luminance image. It will be a grayscale version of this image. And there is something. He's making some comment here. Yeah, this is how to compute this in MATLAB. So this, instead of luminance, it's again the value, because the value is easier to see because it is just the same weight for all of them. So it is easier to take calculations with all of them. And this is histogram, luminance. You can see that there is a change. Maybe for the, even here, if you look at this plate, it's a change between the value and luminance, you see. It's big. So luminance and value, they're not the same. They make sense because the weights are different. Okay, and now he's making a point that is the histogram of the value. So value is an average, okay? So the histogram of the average is not the average of the histograms. Okay, let's look at that. It connects to something that is here. Okay, so remember the histogram as an operator. So the histogram is an operator. So let's say that I have my operator here. I will not do fancy H anymore, but this is a system. Okay, so it is an operator. And then I put R then I will have the histogram of R. I could see I will have the histogram of green. Okay, what if I have R plus G? Will I have this is the question? Will I have HR plus HG? What do you think? Or what?
For example, value for business.
Yeah, we are doing not value or luminance, we are just adding the two. So same weight equal 1. So same weight. So if I add the two signals, will I have the two output?
Depends if it saturates or not.
Yeah, that is one thing. Yeah, these may saturate. Actually, that's a good point. So let's say that my image, this one is full of 200 to 255, and this one, I use a different color. So actually, this one we can use. This is full of 255, and this is green, so it's also full of 255. Now, what are these two histograms? So they will be 255 and all the others to see. This will be, always remember to name your axis. If you make a drawing and you don't name your axis, and it is not complete. And this will be the HG. And then we have this one that is H minus similar. So it has zeros everywhere, except this one is R2. Okay, now I add the two signals. So this one, this is E. And now I will add the two. So I will add the two. R plus E. So the values here will be 510. So what is the histogram? The histogram is 510. And this is not HR plus HT. Okay, so do you know any family of operators that fulfill this thing? You add these two, you have this, which is the family of operators that fulfill that property. Linear operators. So linear operators, if you have a linear system, as example. So if you have a linear system, and I have, let's use the same notation that we use for linear systems. So if you have a linear system like this one, H is linear. So if you have W1, X1 plus W2, X2, so you have a weighted average of two signals, then and X1 is producing Y1, X2 is producing Y2. So Y1 is H applied to X1. This is H applied to X2. Then you know that the output will be this one. You're familiar with linear system, right? All of you? You also? Yeah. Yeah, these people I know, or that's more or less what we study, but I don't know what you have. Okay, so linear systems fulfill this property, but counting is not a linear system. And here we have, that to show that something is not linear or something doesn't fulfill the property, it is enough with a counterexample. So this is the counterexample that this is not true. So counting is not linear. So the histogram is not a linear operation, and yeah, so the histogram of an average is not the average of the histogram. Also, this sounds a little bit like that. I don't know how to say, like a password or something. I don't know. How do you say trabalenguas in English? But, okay, so you have two operations. You have average, and you have, let's have two linear operations. Let's have first two linear operations. So H1 and H2 are linear. Okay, so H1 and H2 are two linear operators. So they are linear. You start with X, here you have Y. You know that for linear operators, you can combine your operators. And do first H2. And then you will still get Y. So this commutative of the property is something coming from linear. So linear are commutative. They are not the only ones, but all linear systems, they are commutative. In general, some of them they are commutative, but in general, non-linear operators are not commutative. So if we have two systems, like the ones we have, so if you have a couple of systems, average, the histogram. This one is linear, but this one is not linear. This one is not linear. So they don't commute in general. So it is not the same computing the average and then the histogram, or computing the histogram and then the average. Okay, and then, yeah, this is MATLAB code. We don't care about MATLAB code. And yeah, this about this we care. And I think it would be simpler to have it here. Okay, so this was the histogram. Okay, what is the histogram? We can let us. So histogram was simply counting. Okay, so we have to add it. So we have an image, and the histogram operator was in the histogram was simply counting. What if instead of counting, I define the normalized histogram? The normalized histogram will be the previous histogram divided by RC. I divide by the total number of pixels. So actually, let me be a little bit. So we have this like this. So we have a histogram, a standard histogram, but now I multiply by 1 over RC. This new operator, this is a new system. This new system will be called the PDF system, probability density function. Okay, so what is this? So now instead of so let us look at one specific result. So let's look at I have have an image, have an image of 255 everywhere. Now this one here, this intermediate side, the this is histogram by, okay, and this we are seeing, but the normalized one that I will call it PDF of I 0 everywhere, except this one that will be 1. Always label all your sketches, okay? So this one will be 1. And what is it? It is, what is the probability? So this is the definition of this is the probability of the image I at a particular location taking the value G. Isn't it? So if I take at random any position in this image, what is the probability that it takes value 255? It's probability 1. It's the probability that it takes any other value, 0. And in general, that is the interpretation of this PDF. So the PDF is, if I take, this is the normalized one divided by the number of pixels. So if I take any pixel at random, what is the probability that it takes value 50? 0.005. This is the probability that it takes value, I don't know, 255, or whatever. Okay, now this is called probability density function. And you may remember there was something called cumulative density function. So the cumulative density function, density function I, the given G, is the probability of that taking a value that is smaller or equal G. So this is very easy. This is simply, I have to add all these probabilities. So let's say that I have value G, I don't know, 200. So then I have to go, it's the probability of taking value 0, what is the probability of taking value 1, 2, up to 200. So I can rewrite that in this way. I can say, this is the sum of G prime from 0 to G of this probability. I will use the PDF because it is simpler to write. So of the PDF I value G prime. Okay? So I simply have to sum all the probabilities. Good. Okay, now, does it sound like something familiar to you? So let's say that now I have this system. I have this system that takes an image, goes through the PDF, and I want to put something in here such that all this is now the CDF system. Then I have here CDF. What should be that system that I need to put there? Do you remember that? You have to convolve the step function. Do you remember the step function? Of course, this function. That's me. Suppose. Do you remember this step function? So if you convolve with this function, this is the effect. You are summing all the previous values up to that point. Now you have a new system that computes cumulative density functions. I want to undo it. I want to put something here. It's a different color. A CDF. And I want to do something here such that the output is again a PDF. And I recover. So once I have integrated, this is a kind of integral, right? So this is a kind of integral. The summation up to a point is a kind of integral. So what can I put here such that I can undo this summation? So a couple of techniques. So you have to convolve with this function. That convolution you can also write in this one. So let's say that I convolve with 1. So I convolve with 1. So let's use so PDF of G will be a CDF of G. So if I convolve CDF of I with a delta, what I have is CDF of I, no? And then minus this convolution. Do you agree? And it makes sense. This is everything up to G. So if I want to recover the one at G, I have to take this everything up to G minus everything up to G minus 1. And then what is left is just the PDF at G. Okay, so now we have a couple of inverse operators. So this one is the inverse of this one. This one is the inverse of this one. Are they linear operators? Yeah, why? Because
Yes.
we have a convolution. Because convolution is a linear operator, and we are convolving with something. Then they are linear. Okay, so that is what is in this slide. This slide is explaining now. So the CDF is the sum up to a point of all the PDF, and then the PDF is just the subtraction of these two. And then the other one is for continuous variables. So let's say that my image has continuous values. So now it is not discretized to be 0, 1, or 2, but it can take any value in between, 0.75 if we want. So the equivalent definitions or operators are this one. So I have to integrate the PDF from minus infinity to the gray value that I want. And if I want to, so the opposite of integrating is differentiation. So if I want to go from the CDF to the PDF, I have to differentiate. Okay, and now this is how they look like. So the CDF that looks like this. So this PDF was the probability of taking at random a pixel and having a value 50. The CDF is the probability of taking a value 50 and having a gray value that is smaller or equal to 50. So I take a random pixel. What is the probability of having an intensity that is equal or smaller than 50? That is the CDF. And then what about 255? Is the probability of having a value that is smaller or equal to 255? Should be 1. Because all the pixels, they have value between 0 and 255. So it has to go linear, monotonically increasing from 0, not from 0, the probability of 0 to 1. Good. Big question. Okay, so histograms are counting. Simply counting, that's it. Okay, that's all for the theory today. And later after the break, we will see some more things of the practice. Actually, as we have a lot of time, I would like to show you a few things. Okay, so let's make a break of 10 minutes. Come back and go there for 7 minutes. So, if it was-